This is Craig Migliaccio from acservicetech, and today what we're going over is superheat, subcooling, saturation, all the components within a heat pump and air conditioning system coming up. Anytime that you are checking the refrigerant charge on a heat pump or an air conditioning system, what I really want you to think about is the refrigeration cycle and the refrigerant state like over top of the system that you're working on. And it's very important for not only checking the refrigerant charge, but also troubleshooting the system. It's going to allow you to troubleshoot it real quick. And so I just want to give you a quick tour before we head over to step one, which is the compressor inlet. But we have our outdoor heat pump right there. It's in air conditioning mode right now. And so here we have our air handler that's inside the building. We have a thermostatic expansion valve as the metering device at the indoor unit. This one has an internal bypass, and at the outdoor unit we have the compressor. So that's the refrigerant compressor. It pressurizes vapor refrigerant. And in this case we have a scroll compressor, which are very common in comfort cooling, heating, and air conditioning systems, so heat pumps and air conditioning units. And so up at the top we have our refrigerant states, which are our dark blue, and that means it's a low temperature, low pressure liquid. And we have our light blue color, that's our low pressure, low temperature vapor refrigerant. Then we have our kind of like bright or light red, and that is high pressure, high temperature liquid. And then we have our dark red, which is high pressure, high temperature vapor. And so that's going to guide us through this whole thing as we move through this. And so we have our step one, which is the compressor inlet. So we have low pressure, low temperature vapor refrigerant. And so vapor means gaseous state. It just means that there is no liquid. It's not saturated, and saturated means liquid and vapor at the same time in a mix. So the compressor has to have vapor refrigerant entering into that scroll compressor. The scroll compressor's job is to increase pressure so that temperature increases. And likewise, anytime that you increase temperature, pressure increases. So we have a selection of different refrigerants that we use in these systems. We used to have R22, now we have R410A, and now we have new refrigerants coming up, such as R454B. But anyway, the whole point is it's going to increase the pressure of the refrigerant in order to increase the temperature. Step two is the compressor outlet. And so at the compressor outlet, we have high pressure, high temperature vapor refrigerant exiting the compressor. And then what you have is the refrigerant is entering into that discharge line. And it needs to go through that first before entering into the reversing valve. But this is the hottest refrigerant line on the entire system. And that's because it's high in pressure. And so then we have step four, which is the reversing valve. And so in most systems besides root and ream, that reversing valve is electrically energized during air conditioning mode. And so it's not energized during heating mode. And so on root and ream, it will be not energized in air conditioning mode and energized in heating mode. The inside of the reversing valve shifts over due to this pilot valve being energized. And so you have high pressure refrigerant pushing the inner slide on the reversing valve over to the side. And if you want to learn more about that, we have a whole nother video on the reversing valve and the internals and how it works. And so the refrigerant is going to remain unchanged as it travels through the reversing valve. And next, that high pressure, high temperature vapor refrigerant is entering into that condenser coil. So what's happening is that outdoor coil needs to be higher in temperature than the outdoor air. So that's how the refrigerant works. The refrigerant absorbs heat energy from the inside of the building as air is blowing across that coil. And then that refrigerant flows to the outdoor unit where the compressor increases the temperature of the refrigerant by increasing pressure. And then you have that refrigerant rejecting heat to the outdoor air. And so the second that refrigerant enters into that coil at the outdoor unit, you have that outdoor air coming across the coil and then getting blown out the top. So it's just ambient temperature. So say maybe it's 90 degrees outside, and what's going to happen is it's coming across the coil and then it's getting blown out the top. So it's going to be a lot hotter when the air comes out. And so basically you're rejecting that heat energy into the outdoor air. And so maybe the temperature of the refrigerant in that coil is about 170 degrees. And so it's going to be much hotter than the 90 degree air outside. And so next you have your refrigerant entering into the saturated state. And what that means is that that refrigerant has rejected so much heat energy to where now it's doing its phase change. So maybe you have 95% vapor there and 5% liquid. And so at that point, say it's about 105 degrees at that location right there, right where it starts to phase change at. Then you have step 7. And so step 7 is the phase change of the refrigerant, and that's the secret to this whole thing even working. After the refrigerant starts to phase change, where you have liquid and vapor both existing at the same time, that means it's saturated, and then it's going to hold that temperature at 105 degrees as it travels through that coil. And so basically at this point right here, right there, you have 95% vapor and 5% liquid. And then as it moves through, say in the center of the coil, you have a 50-50 mixture of vapor and liquid refrigerant. And then after it comes over towards the bottom of that coil, you have, say, 95% liquid and 5% vapor. And so during that whole time, it's at 105 degrees, which is higher in temperature than the outdoor air crossing the coil. And then after that, you have a fully liquid state. So the refrigerant has phase changed, and now subcooling begins. And subcooling means that the liquid refrigerant is lowering in temperature now. So after the phase change, where it's basically locked in temperature, then the refrigerant is going to start to decrease in temperature in the liquid form. And so now you have the refrigerant traveling through the line. It's still subcooling, it's still rejecting heat energy as it travels through the tubing. Then you have the outdoor metering device. And in this case, during air conditioning mode, that's in bypass form. So basically the refrigerant is flowing through the metering device in the inside and around it. And so there's an internal bypass inside a piston metering device. Now the piston metering device may be located like in the outdoor unit or at the service valve, maybe in front of it. Some units will have a thermostatic expansion valve there instead of a fixed orifice, which in this case it's a piston. So the subcooled liquid refrigerant is going to remain unchanged, and then you have the liquid refrigerant entering into that liquid service valve. So the temperature decrease between where the refrigerant turns into the fully liquid state in the condenser coil and where it comes out of the liquid line service valve, that is referred to as a subcooling when we're checking the refrigerant charge during air conditioning mode of an air conditioning unit or a heat pump. And so in this case, let's just say it was 93 degrees at the liquid line service valve. So you have 105 minus 93, and you're left with 12 degrees of subcooling. And so that's really what you want to pay attention to. Then the thing that you also want to pay attention to is the outdoor unit rating plate. And so the rating plate will say the TXV subcooling of whatever the refrigerant is. So it'll say R410A subcooling 12 degrees or 10 degrees or 14, whatever that you're shooting for. So if this rating plate said 16 degrees of subcooling and you had 9, then what you're going to need to do is probably add some more refrigerant in order to get the subcooling to increase. When you add refrigerant, your saturated temperature is going to increase and your liquid line temperature is going to decrease. And then that spread is called the subcooling. All right, so now you have subcooled liquid refrigerant. It's heading through the line set. So where you have the outdoor unit connected to the indoor unit, that's referred to as the line set. The small tube is the liquid line, and the large tube is the vapor line. Now, it doesn't matter whether this is an air conditioning mode or heating mode. You can still refer to them in the same manner because it's just a directional flow of the refrigerant. The vapor line's still going to have vapor traveling through. The liquid line's still going to have liquid traveling through. It's just going to be, like on the vapor line, it'll be higher in temperature. It'll be the discharge gas. Anyway, we're in air conditioning mode now on the liquid line. The liquid refrigerant enters into a bi-flow filter dryer. A bi-flow filter dryer means that the refrigerant can flow in either direction, and inside the filter dryer, there's desiccant in order to absorb any water that's inside the tubing, so any water vapor. And the whole point of trying to trap the water inside the filter dryer is to not allow the water to mix with the refrigerant oil in the system. In a R410A system, you're typically going to have POE oil, unless you're on a mini split system where you may have PVE oil. But in this case, you have a comfort, cooling, air conditioning, or heat pump system, so it's going to be likely POE. And that is very hygroscopic. That means, that's a fancy word once again, for it means that it really grabs the water. And the problem with this is that POE oil mixed with water is going to create alcohol and acids. When that happens, you have to also remember that the refrigerant is flowing through the entire system, and the refrigerant is traveling into the compressor. Refrigerant and oil travel together through the system. And the refrigerant, since that Scroll compressor is a hermetically sealed compressor. That means it's a welded shut compressor. Once again, that's a fancy word, hermetic compressor. It's on the EPA 608 exam. A lot of the stuff that I'm telling you, it's all terminology that we use in the field and on the EPA 608 test. So what you need to think about is that refrigerant and oil travel through the entire system, and the refrigerant's job inside the compressor is to cool the motor, because that scroll compressor is a hermetically sealed. That means it's welded shut. And so that refrigerant is going to be touching the electrical motor windings. And so each wrap of the motor windings, you're going to have refrigerant passing over that to cool it. Well, the thing is, you're also going to have oil mixed with the refrigerant passing over that. So if that oil is acidic, it's going to wear down on the resin that's separating each of the wire loops on the compressor windings. And if you have acidic oil, it's going to eventually lead to a compressor burnout. It's just going to break the motor. It's going to allow it to short, and you're going to have a big problem right there. And you're going to end up with soot, basically carbon, all through the inside of this system. And so you want to avoid that. That's why anytime you open up a air conditioning or heat pump system, replace the filter dryer. That's why when you braze on a filter dryer, that's the last thing that you install on the system, because you don't want any contaminants going into that filter dryer. So anyway, the refrigerant flows through there, and it remains unchanged. And then you have your high pressure, high temperature liquid refrigerant. It's subcooled, that enters into the thermostatic expansion valve. So that's a TXV. And so what's going to happen is your refrigerant is going to lower in pressure. When you lower in pressure, you want to remember that it's going to be also lowering in temperature as well. And so if you have, say, 93 degree subcooled liquid refrigerant entering into the TXV, on the other side, you may end up with something around, say, 42 degree liquid refrigerant on the low side of the TXV. And so there's a pressure reduction that's happening. It's an orifice size that's inside the TXV. You have to remember that the TXV's job is to maintain superheat across that coil. We'll be getting into that in a second. But really what's happening is once the refrigerant, you have high pressure liquid, basically goes in through the TXV, you want to think about it kind of as like a squirt bottle. You have liquid in the bottom of the squirt bottle, and then you're pulling the trigger, and then it's squirting out. So it's primarily going to be liquid exiting, but you're going to have a little bit of vapor at the top. So maybe 80% liquid, 20% vapor, flash gas. And so you're already in the saturated state as you enter into that indoor coil. So on a heat pump, we would just call that the indoor coil. During air conditioning mode, that indoor coil is going to act as the evaporator. And so during heating mode, it'll act as the condenser coil. But anyway, in this case, we have 42 degree, low temperature, low pressure. We're just going to refer to it as liquid refrigerant entering into that evaporator coil. Now, you have saturated refrigerant. You're already saturated, right? So you're going to, say, maintain 42 degrees as you're traveling through that whole coil. Once you enter the middle of the coil, you're going to be still at 42 degrees. And so you're just going to be at 50% liquid, 50% vapor. As you get towards the end of that coil, you're going to have, say, 95% vapor and 5% liquid. And then in step 16, you're going to have superheating begins. And superheating, fancy term for vapor refrigerant, is increasing in temperature. Okay? So as you have your air crossing this coil, you may have, say, 70 degree air crossing the coil, and you may have 42 degree refrigerant coming across the saturated state. And over on the supply side of this evaporator coil, you may have, say, 50 degree air now, say, coming out of the supply registers. And now as the refrigerant is traveling through this vapor line, it's increasing in temperature. So we have step 17, superheating continues. It's traveling through the indoor evaporator coil. The refrigerant is absorbing heat energy from the air, and it's also attracting any humidity onto that coil, which then it's going to drip into a pan, and then it's going to be piped maybe out right outside on the ground. And so next thing you're going to have is you're going to have your superheat. So if you have 42 degree refrigerant at the end of where the saturated state is, where it comes out of the coil, meaning the refrigerant, the vapor refrigerant comes out of the coil, it has risen to maybe 54 degrees. So 54 minus 42 is 12 degrees of superheat, and that's the job of the TXV, is to hold that superheat steady regardless of if that unit, the outdoor unit, has maybe, say, 5 degrees of subcooling or 20 degrees of subcooling. And you also have to remember that as the temperature increases outside, you may have a slightly higher subcooling, and the TXV is just going to try to maintain this thing. So if you have a dry climate, like maybe you have a very, very low indoor wet bulb temperature, its job is to still make sure you have vapor refrigerant exiting that indoor coil, and then it has some superheat. So as long as you have some subcooling, meaning you have liquid entering into that TXV, if you have, say, 12 degrees of subcooling, you don't have any saturated refrigerant entering into this TXV. You have solid liquid. Same thing, if you have 12 degrees of superheat on the vapor line, you know that it's fully in the vapor form as it's then traveling to the outdoor unit. Now, when we're checking the refrigerant charge, we're not typically checking it right at the indoor coil. What we're doing is we're taking a pressure measurement on the vapor line and a temperature measurement on the vapor line in order to calculate our total superheat. And so what's really happening is we're measuring the pressure in order to convert that to saturated temperature to determine the temperature of the refrigerant in the middle of the coil. So in this case, it's 42 degrees. And if we were to measure our line temperature, that's going to give us the temperature of the refrigerant traveling through the tube. In this case, it's 54 degrees. So that means we have, say, 12 degrees of total superheat. So if this system had a piston here, then we would check the refrigerant charge with a total superheat method. But since the indoor coil, the active metering device, is a thermostatic expansion valve, we're going to check the refrigerant charge with subcooling. And so the whole job of the TXV is to make sure that it has some superheat. Now, the whole point of this is what I want you to think about is you could be having a problem here. If you had very high superheat, but you had the correct subcooling, then that would probably mean that you have a liquid line restriction, meaning that this TXV is not operating correctly. It's stuck in the almost a closed position. And that might mean that the thermostatic expansion bulb and line has leaked refrigerant, and it can no longer allow enough refrigerant into that coil to absorb the heat energy from the air inside the building. The whole point of me saying this, and I know we have other videos that you can check out, the whole point of this is that I want you to check both subcooling and total superheat anytime that you are checking the refrigerant charge or you're adding refrigerant to a system. So it's not good enough to just make sure your subcooling is correct. You want to make sure that your TXV is doing its job properly, and a residential, commercial, or any type of air conditioning TXV is going to have probably around 8 to 14 degrees of superheat already factory preset with the spring pressure on the bottom of the TXV. Then we have a whole nother video on how that thermostatic expansion valve works and the 3 pressures applied to that TXV, so make sure that you check that out. So we actually show the whole pin moving and everything on the inside, so make sure you check that out. So anyway, you have your vapor refrigerant entering back into the outdoor unit through the vapor line service valve and up into the reversing valve. So there should not be any temperature change really across that reversing valve, except for the fact that you got to think that that body of the reversing valve and the fact that the refrigerant is flowing next to each other, there's going to be a little bit of a temperature exchange there. And so it's not going to be absolutely 100% exact when you take a measurement across the vapor line coming into the reversing valve and the center tube coming back out. It may be 0.5 degrees off from each other. The other thing to think about is anytime that you have your reversing valve, then the single tube on the reversing valve, you can have a single tube on one side, 3 tubes on the other side. The single tube is always a discharge from the compressor. The center tube on the other side, where there's 3 tubes, that's always the suction line going to the accumulator or to the compressor. You have the vapor refrigerant entering into the accumulator tank, and the job of the accumulator is to safeguard the compressor, and it's also to be a storage vessel for the liquid refrigerant when it's not needed as much. And so in this case, you're going to see that accumulator tank is primarily drained of any liquid refrigerant in air conditioning mode. It's basically using up all the refrigerant in the system. So there's a little bit of liquid on the bottom of that accumulator tank. There's also a metering device at the bottom in order to Basically, if there's any oil that gathers in the bottom of that accumulator tank, it meters it back into the compressor along with some liquid refrigerant. But the metering device allows just a little bit to enter, and then it to phase change right into a vapor before it enters into the compressor. But then after the refrigerant goes into the accumulator tank, only vapor is allowed out of that accumulator tank. So just say you had a problem with your TXV and maybe you had low indoor airflow and the TXV is not able to close down the amount of refrigerant entering into that indoor coil. If you had a problem and the refrigerant was still saturated as it's coming out of that coil, the saturated refrigerant, meaning liquid and vapor, are not going to enter into that compressor. That accumulator tank is going to safeguard the compressor and only allow vapor refrigerant to exit that tank and enter into the compressor. And so that's how this really works in air conditioning mode. And now I want to take you over into heating mode and explain what's happening there. Now we're in heating mode. So this is with the reversing valve pushed the other direction in order for the refrigerant flow to change. So if you're looking for these PowerPoints, we do have these available over at acservicetech.com for HVAC teachers. And there's presenter notes in there so you can read right along. But anyway, I'm going to get into this now. So you still have your low pressure, low temperature vapor refrigerant entering into that scroll compressor. And so then you're going to end up having your high pressure discharge gas exiting the compressor. Next, the discharge gas, it's the hottest temperature refrigerant in the entire system. It's going to be flowing over to the reversing valve. It's going to remain unchanged as it goes through the reversing valve. Remember, on most systems, the reversing valve is not energized, so it's naturally going to be sitting in this position without any energy going to that pilot valve coil. And so the high pressure, high temperature vapor refrigerant discharge gas is going through the reversing valve, remaining unchanged, going through the vapor service valve, remaining unchanged, and now the discharge gas is flowing over to the indoor coil. Very important to have your insulation on there. It's very, very hot. And so you have your high pressure, high temperature vapor refrigerant entering into the coil. It's not hitting your metering device, it's going right into this coil. Now this coil is acting as the condenser coil. It is allowing the refrigerant to reject heat into the air. And so it really depends on what the outdoor air temperature is and if the outdoor coil is frozen or not, or has frost on it or not, as far as the temperature exchange at the outdoor unit and the indoor unit. Remember that anytime that your outdoor air is, say, 40 degrees or lower, your refrigerant in the outdoor coil is going to have to be probably lower than the temperature that water freezes at. So it's going to be below 32 degrees. And that's going to attract any humidity that's in the air flowing across that coil. The humidity is going to get stuck on the coil and it's going to start to frost. That's going to happen. You got to think that we're going to be running these heat pumps below 40 degrees. And so there's a whole defrost cycle, and I go over that in another video. I go over all the steps that occur, so you can follow right along with that. And that's linked down in the description section below. But anyway, you have your hot discharge gas flowing through this indoor coil. As it's flowing through, you are de-superheating. Remember, that means that the vapor refrigerant is lowering in temperature as the air is crossing across that coil. Then you have your saturation occurring. So it's basically rejected so much heat energy to where now it's becoming, say, 95% vapor, 5% liquid. Then in the middle of the coil, it's a 50-50 mixture, 50% liquid, 50% vapor, and then it's going to then become fully in the liquid state, and that's where your subcooling begins. So you are rejecting heat energy, and just say that it was a warm temperature outside. So say it was 60 degrees or 55 degrees outside. You may have what's called a condenser cycling switch. It looks like a little pressure switch at the outdoor unit. And what's going to happen is you might not be able to reject enough heat energy at this indoor coil in order for the pressure to not just continue to climb at the outdoor unit. And so it's going to work too efficiently, if that makes sense, you know. So it's going to absorb too much heat energy when it's real high in temperature outside, and your indoor fan is not set at a high enough speed a lot of times in order to allow the refrigerant to fully reject all of the heat energy. So once your refrigerant is fully in the liquid state, it's going to start to subcool, and that means that the liquid is going to then lower in temperature as it's flowing through that indoor coil, which is now the condenser coil. You're rejecting your heat energy into the air. You may only have a 10 or 15 degree temperature rise across this coil, and you're going to have your blower still at a fairly high speed in order to move any heat energy across that coil and basically absorb the heat energy from the refrigerant as the refrigerant is rejecting the heat energy. It's basically locked in a temperature that is higher than the air temperature crossing the coil once it begins to subcool. So a heat pump may not feel comfortable in the wintertime because the blower motor is going to be at a high fan speed, and it's going to have that evaporation effect on your skin. You're going to have a lot of air moving in the building, and that's going to basically dry your body out. It's going to cool your body, and so that's an evaporation effect. So it's going to make you feel colder. Remember, coldness is just a feeling. We don't refer to this stuff as cooling necessarily because it's not doing that. Cold is a feeling that we have. So we're going to feel a little cold, but the temperature is rising in the building. It's going to flow through the inactive metering device. So there's a little ball here on the metering device which is going to rise and get up out of the way, and the liquid refrigerant, the subcooled liquid refrigerant, is going to flow through the bypass of the TXV. Now, the older TXVs had a little tube bypass that it went around the TXV, and there was a little plate down here at the bottom, and it kind of flowed through the spring area. But on the newer ones, there's a little ball on the inside or a cylinder that pops up or down. Okay, so you have your high pressure, high temperature, subcooled liquid refrigerant is then entering into that filter dryer. Remember, the filter dryer's job is just to trap and absorb any moisture in the system, and it also has a pre-filter as well, but on a biflow, has a screen filter on both sides, but that could end up getting dislodged now that the refrigerant's heading in a different direction. It's mainly the desiccant that we're concerned with. It has a limited capacity. So if you have a lot of water vapor in this system because the vacuum job, like the vacuum pump procedure, was not done very well, this filter dryer is only going to have a limited capacity to store moisture. So if that's completely filled, it's no longer going to protect the compressor. And so if you were to ever replace the filter dryer after recovering the refrigerant out or pumping the system down, you have to remember to cut these out. Don't unbraze them, otherwise you're going to be allowing the moisture to get back into the system. Now you have your high pressure, high temperature subcooled liquid refrigerant entering into that liquid line service valve. Now on this system, you see there's two service valves. There's also going to be a little access port on the true suction, and that's at the accumulator line, the accumulator suction line, where it's going into the compressor. And so you're typically going to see 3 ports on a heat pump. And so during heating mode, you could attach to that in order to see your true suction pressure. So next, you're going to go into the active metering device. And in this case, it is a piston metering device. In this case, you see the piston metering device is downstream of the liquid line service valve. Sometimes it's right in the nut in the front of the liquid line service valve. So you got to remember that if you're attaching your gauge set onto that, or your test probes. And so this piston metering device is inside the outdoor unit after the liquid line service valve, and it's going to push in this case, it's not a TXV, it's a piston chamber. It's going to push the piston up against the edge, and the refrigerant's only going to be allowed to flow into the middle of the fixed orifice piston metering device. So you're going to have a pressure drop across that metering device. When you have a pressure drop, temperature is going to lower as well. So now you have a low pressure liquid. It's basically 80% liquid, 20% flash gas, and you're already in the saturated state. So if you're at, say 30 degrees in that coil and you're at 40 degrees outside of the coil, you are now basically at a lower temperature than the outdoor air, and you are going to be locked at that temperature through this saturated state where you have 50-50 mixture, 50% liquid, 50% vapor. And then you have where the refrigerant turns into 95% vapor and 5% liquid. And so you're still at a lower temperature, at the same temperature you have been the entire time while the refrigerant's flowing through the coil, as the refrigerant is absorbing heat energy from the outdoor air. You have to think about this, like if the refrigerant didn't phase change and it just was vapor all the time, you'd be able to absorb like no heat. You have to think that the saturated refrigerant and the phase change, That is the secret to this whole thing happening. And you could think about maybe an ice cube, like think about 32-degree water. How long is it going to stay 32 degrees if it's just water and you're drinking it? If you have it outside, it's a hot day, you know, it's going to rise in temperature. But an ice cube is going to go through a phase change from solid into a liquid. And so it's going to be able to hold at the 32 degrees a lot longer. So the amount of BTUs of heat energy that refrigerant is able to absorb from that low temperature air is significant, even though you have cold air outside, or it feels cold. All right, so now you have your superheating begins, where you have the vapor refrigerant is now starting to increase in temperature. And so sometimes when that coil is completely frozen solid, you're not going to have any superheating. So no superheating, and the refrigerant is just going to remain saturated as it goes into the accumulator, but I'll get to that in a second. So let's just say the coil has a little bit of frost on it, and everything's working fine. You're going to have some superheating, and superheat means that the vapor refrigerant is increasing in temperature, and the vapor refrigerant is traveling through the reversing valve, remaining unchanged. And by the way, if you're ever wondering if that reversing valve is partially stuck, that you can take a temperature measurement across 2 of those 4 tubes. The tubes that you're going to measure are the center of the 3 and the other low pressure, low temperature line. You're not going to measure the high temperature lines. For one thing, they're so hot that you could damage your K-type temp sensor or whatever you're using, potentially. The other thing is the lower temperature lines are closer to the air temperature outside. So there's going to be less occurrence of any errors happening when you're taking your measurements. Because if you're taking your high pressure, high temperature measurements, and maybe one's not as insulated as the other, you didn't put any Armaflex insulation around the tube after you put your temp sensor on, it's going to lead to some big inaccuracies. You may see 6-10 degree temperature difference, and that's just because you didn't insulate one of the 2 temp sensors, or it fell off or something like that. Remember to stay maybe 6 inches away from the reversing valve when you are taking any temperature measurements across there. There really is no magic number of saying, hey, the reversing valve is bad because you have a temperature exchange. You know, if you have 20 degrees and you're on the low pressure, low temperature lines, those 2, yeah, the reversing valve is not fully seated all the way to one side. Maybe there was some debris inside. Maybe there was a compressor burnout and somebody replaced the compressor but not the reversing valve. You know, maybe the filter dryer was never changed, or maybe there's not even one on it. There's a variety of things that could have happened. Maybe somebody heated up the reversing valve when they were brazing it in or something like that. A reversing valve is normally going to be factory installed on this heat pump inside that outdoor unit. So anyway, you have your vapor refrigerant traveling into the accumulator. Like I said before, if you have a frozen outdoor coil, the refrigerant may have never changed into the vapor state and may have never superheated. And so you have saturated refrigerant entering into that accumulator. You're also going to notice that there is more liquid refrigerant in the bottom of that accumulator tank, typically during heating mode, because the system isn't running all the refrigerant through the system because that outdoor coil has frost on it a lot of times. When we're running these things, an outdoor unit, like an outdoor ducted heat pump, you're only going to be able to run it down to a certain temperature, and then you may have to switch over to some other auxiliary heat source. It's just a matter of how efficient your defrost controls are on your outdoor unit. A mini split unit runs very, very efficiently with its defrost at the outdoor unit. It runs very efficiently also with absorbing heat energy at that indoor coil because it's not ducted. But that's a whole nother subject. This is a ducted heat pump unit in heating mode. So anyway, you have your refrigerant entering into the accumulator tank, where the accumulator's job is to store any liquid refrigerant, and its job is to also make sure that only vapor refrigerant exits the accumulator tank and enters into the compressor. So it's very, very, very important to have an accumulator on a heat pump, just because that outdoor coil might have frost or ice on it, and if you didn't have that, you would basically immediately be killing that compressor with liquid refrigerant entering into it constantly. That would, not only can the compressor not really pump liquid refrigerant very well, It's also going to lead to a lack of lubrication on the inside where the metal plates basically are rubbing up against each other. And it's going to wear down so bad to where that compressor is going to fail. And so then you just have your vapor refrigerant entering back into your compressor again, and then that cycle starts all over. So if you want to learn anything else about air conditioning, refrigerant charging, make sure to check out some of the other videos that I have linked down in the description section below that are related to this. We have our PowerPoints available over at our website over at acservicetech.com. Also, make sure to check out our Refrigerant Charging and Service Procedures for Air Conditioning book. We have a 1,000-question workbook, and there's also a self-study guide with an answer key so you can check your answers to make sure that you're understanding them very well. And then we also have quick reference cards that can be used out in the field. You can throw these right in your service pouch. They're not cardboard. They are polystyrene. They'll hold up very well, even with refrigerant oil and heat and sunlight. So we made them and tested them. And so the other thing is we have troubleshooting a chart right here, which that's the whole point of what I'm saying. Whether you use a digital set, test probes, analog or compound gauges, anytime that you are checking the refrigerant charge and measuring your voltage, your current, just doing an overall check. It's very important to think about the refrigeration cycle and what your measurements really mean. And we also have this troubleshooting guide to help you along with that. So if you have high pressure or low pressure on the vapor line or the liquid line, your superheat or subcooling is high or low, your amps are high or low. You know, if your indoor coil is frozen when you arrive to the site, it's going to be able to help you diagnose those problems. So make sure to check all this stuff out over at our website. We also have these physical products available over on Amazon as well. We also have them as posters, and those are available over on Amazon and at our website as well. They're in a lot of schools across the country, which I'm thrilled about. And so the students in the classroom can look up at the posters and kind of visualize what's happening. Some teachers are putting them right over the units that they're checking the refrigerant charge on inside their shop. That's huge. That's awesome. And so the whole point is about transmitting any knowledge that you have to newer technicians that are hungry to learn so that they can provide for their families well or their future families well. And that's the object of all of this stuff. So I hope you enjoyed yourself. Make sure to also check out some of the other articles that we're constantly posting over at the website over at acservicetech.com. Hope you enjoyed yourself. We'll see you next time at AC Service Tech channel.